I'm Dan. I'm pumped to be here and talk about kind of what I've been working on for actually a year now. And that's been bringing VA lists, which is a C structure, into Rust. And so I'll kind of be talking about that and ultimately why you should not do that and why you should not use VA lists in Rust. So the disclaimer here is that there's going to be a lot of unsafe here. It's very, very unsafe. And there's also going to be a lot of C. So before we really get into using VA lists in Rust, I figured I'd take a step back and talk about just using VA lists in C. So a little bit of background if you haven't really written much C or used VA lists before. It's a type that's used as a parameter to retrieve a variable number of arguments from a function. It's defined in section 716 of the C standard, and it's available in the stdarg.h header. So C isn't like built by one compiler, right? Like there's lots of different C compilers. It's very much standardized and everything. So this is you can read all about it in the C standard. So briefly go over the API that's defined in that header. There's the VA start function, and that's used to initialize the VA list. VA arg, which is a function that's used to retrieve the next argument of a given type from the list. VA end, which is essentially like the garbage collection routine. So that's what you use after you're done using the list. And then VA copy, which that copies the list state to another list that's given to the function. That's the core functions that are available in C. But that probably doesn't really make much sense, so I figured we should probably go through an example. So super simple, like one of the most simple examples you can come up with is, let's define a function add n that will return the sum of up to n integers passed to the function. Here we have the function add underscore n. 3 would be the n parameter. And then, so we're going to add up the next 3 arguments that are passed to the function. So 10, 15, and 17, add it up. My math is right. That's going to be equal to 42. So let's get into the implementation. So add in the initial structure is going to look kind of something like this. So you're going to include stdarg.h. That's kind of similar, if you haven't written C before, that's kind of similar to like the use statement in Rust. So that's going to make all the functions that you can use with the VA list available to you, and it's also going to make the VA list structure available to you. It's going to define all that. And then the add n function signature, I notice we have just a plain int n here. But then we have the ellipses after that. And that's what you use in C to kind of declare that, hey, this is where a variable list of arguments are going to occur. So then we'll declare some local variables. So we'll declare our AP, which is going to be our VA list, and then a temporary return value. And then we're going to initialize the list with VA start. So notice here the AP, which was our uninitialized VA list, we're going to pass that as the first parameter. And then the second parameter is the last argument that occurred before the variadic list of arguments occur in the function signature. So right here, we only have int n. But if we had int n and then int y after that, then we wouldn't pass n here in VA start, we would pass y. That's kind of tells VA start kind of where to start, more or less. And then, so after we initialize that VA list is going to contain all those arguments. Then what we'll do is we'll pass that sort of initialized VA list onto another worker function, along with the number of arguments that were in that list. And this is sort of like a standard thing you'll see whenever you're using functions or working with functions that have like a variable number of arguments. So printf, if you've used C much, has the dprintf function. So that's kind of a common theme you'll see. And then, so after we call that v add n and collect the result, Then we're going to call VA end and clean up and return. So really, this function, all it is just VA list management, right? Like there's no like actual work going on here. So does that sort of make sense? Questions about that? Feel free to stop me like as I go through this too. This is a good sized group for like questions and stuff. So then let's get into the sort of how v_add_n is implemented. We're going to return an integer. That's going to be the integer that's the sum. We have int n, or the number of arguments that were in the list. And then we have the initialized VA list as the second argument. So we're going to loop up to n times. And then we're going to call va_arg and append the result to our accumulating variable sum. Notice that in the second, so the first parameter is going to be obviously our VA list. And then the second parameter is the type of the argument we want to fetch from the VA list. So I've been referring to va_arg, va_copy, va_start, and va_end, I think was the one I didn't mention, as functions. They're actually not functions, they're macros. So that's essentially how you'd write add_n in C, and that's sort of how you work with VA lists in C. Cool. So now let's talk about VA lists in Rust. So first of all, it's kind of important to understand why that's important, and why it took a year to do this, right? It took a year of my life to implement this. So Rust can currently call any possible C interface. So that's a huge deal, right? Because there's a ridiculous amount of software that's written in C, C++, and there's a huge amount of stuff that uses the C ABI. It's really, really important, and that was achieved. So Rust can call any possible function that you define in C. And
does it still clean out the garbage memory, even if it calls a C interface?
So like if it depends on like what you're talking about. I mean, if you malloc in C and then you don't end up like it kind of depends on your situation. Like we can talk afterwards about that. But it can almost export any interface for C to call. Think about it like almost any C function signature that you could define, you can, almost all of them, you could also define in Rust. However, variadic functions represent one of the last remaining gaps in those kind of list of C function signatures that you cannot define in Rust. And still to some extent currently today. I'm still working on it. Why is that important? So there are actually a ton of functions that actually use va_args. Some really common ones like fcntl, printf, and exec, and a whole bunch of other ones. So it's really, really important that we're able to do that. And I specifically started doing this because relibc, which was an attempt to write a libc in Rust, they have a whole bunch of C in there still because you can't do this in Rust. And obviously fcntl, printf, and exec all are part of libc, so you have to be able to write those in Rust. So.
Before you had va_arg.
Oh, so va_args have pretty much always been there in C. Okay. But this is va_args in Rust, right? So we're trying to write this in Rust. And still, I think you can compile it, but you'll get like lots of like warnings and stuff. Good question. Any other questions? Awesome. So why not? Like, why hasn't this been implemented yet? There are lots of vulnerabilities that are associated with VA lists. Not even just like, a few vulnerabilities, there's entire classes of vulnerabilities that are associated with this. CWE 134, which is format string vulns. So that's specifically having to do with like printf and stuff, those sorts of functions. And then CWE 134, which is essentially more or less calling va_arg too many times. And we'll kind of get into that later, and we'll talk about that. In short, VA lists are incredibly unsafe. So that's why Rust has not implemented them yet. And it was intentionally left out of the language. So the Rust implementation. So it was all defined in RFC 2137, which was written by Josh Triplett. And essentially, we wanted the interface to look something like this. So we have this struct VA list that's going to have like some fields, and then you're going to be there's going to be methods implemented for the struct arg, which is going to be equivalent to va_arg. So it's just going to retrieve the next argument from the list, and copy, which is going to take a closure, and then it's going to give that closure a copy of itself. And then it will return the result of that closure. And interesting notes, you'll notice that there's no way, due to the way the lifetimes are implemented here, there's no way for the VA list that we copied and passed to that closure to escape from that closure. We'll get into that a little bit more later, but that's just a cool way that we're able kind of to make that specific use case of VA list a little bit more safe. All right, so let's, so currently we actually cannot implement the straight add_end function in Rust. I'm currently working on that right now. So currently we can only implement the v_add_end portion of this. So we'll kind of go over that. So this is actually just v_add_end in Rust. So first of all, you have to enable the C_variadic feature. This is still highly experimental. It was only merged like a month ago or something like that. And then the struct is defined in std ffi va list, or if you're in a no std environment, it would be core ffi va list. So we'll define the worker function. So first note, since we're going to be calling this from C, I don't know if you guys have done much FFI stuff in Rust before, but we want the function to actually be named v_add_end. So we're going to use no mangle. So we don't want the function name to be mangled. It needs to be public, right? Because we're going to call the function outside of this. It's definitely got to be unsafe. And then we want to use the extern C ABI. Pretty much the arguments of the list are pretty much exactly the same as C. Any questions about that? Cool. Then loop, the loop, that's pretty much going to be the same. So then in order, inside the loop, pretty much all we're doing is we're just calling the arg method on the VA list, and then giving the type of the argument that we want to fetch from the VA list. Any questions about that? Kind of dig into this more. Awesome. So we did it. We wrote v_add_end in Rust. Can I leave? But before, so let's just talk a little bit about some of the API considerations. So something that's kind of something you wouldn't really notice. So actually, it's defined in the C standard that you can't use va_arg on any type smaller than an int for an integer, and it can never be a float. So that's any integer smaller than 4 bytes is invalid when using va_arg. And also like F32 or 32-bit float, that's also invalid when using va_arg. So if you were to do something like this in C, you'll either get garbage or a program abort. Note, GCC and Clang will throw a very hefty warning if this were to be in your code though. So anybody who actually did this, it would just be, yeah. I can't remember the exact, now I'm assuming it has to do with alignment, but we'll get into like nitty-gritty details of some of that later. We can talk about that after, but that's something that, you know, as I was implementing this, I'd never noticed that before. So in Rust, then when we implemented this API, we wanted to make sure that if you ran this, if this was in your code, we didn't just give a warning, but that we made a return a compiler error. If we could just show this real quick. So we made sure to implement the va_arg safe trait. So this is the implementation in Rust. There we go. So essentially, what we did, I don't know if you guys can see this, but we made a private module and then put a public trait inside of that. And then we implemented that trait for all the types that we wanted to be the va_arg to be able to call it. Hold on. Does that make sense? However, you'll notice we implemented it for I8 and I16, but those are definitely smaller than 4 bytes, right? Whenever in the code generation, whenever you use VA list, the VA list arg method, we actually we promote it to a 4-byte integer and then truncate it back to the smaller one. So if you were to call AP arg with an I8 there, you'd actually be calling AP.arg I32 and then truncating it back to an I8. After thinking about this, I probably could have done the same thing with floats and done an FP trunk, but I didn't think about that whenever I was writing it. I'm not sure why I did that for integers and not floats, but follow-up issue, I guess. What's up?
I don't know if I don't know about float kernels, no, but is that actually months?
No, it's you definitely lose a little bit. So maybe that's why I did it. I don't know.
That's a good reason. That was really good.
Yeah, that was a really good reason. Yeah. When in reality, I probably just forgot. So no, this is not yet implemented yet. So this is sort of what we want implementing the real add-end functions to look like. We're still nailing down some of this. Notice everything is pretty much the same. Note that you can only use this with extern C and unsafe. So we really did not want to put this in the language, but if we had to put it in the language, we only wanted to put it in the language if those two conditions hold, because yeah, it just doesn't really make sense. Yeah, you can use the ... but notice we don't have to use any of the VA start or VA end functions. I'm currently working on automatically inserting those so that you never have to deal with like an uninitialized VA list. Yeah. No, so that's going to be part of the syntax. So we're currently like changing the syntax to, there's a few things that we're kind of nailing down. It'll look something like this. It may not look exactly like this. There's actually a little bit of a debate going on right now, but yeah, there'll be like an actual change to the syntax where you can do this ... and then that's a variadic list. You can do this currently actually if it's a foreign function. So like we talked about earlier, how you can call any C interface. So it's a variadic C function. You can, do the extern C, but it's not, you can't currently like write a variadic function in Rust. Does that make sense? Yeah, it's the Wild West. You can call any type. Yeah, it's the Wild West, and we'll dig into that a little bit later. Yeah, VA lists they're the make files of function arguments. Well, another consideration, the consideration here whenever we designed this was that we wanted to make sure, or Josh Triplett wanted to make sure that you never were dealing with an uninitialized VA list, that was automatically inserted by the compiler so that you didn't have to like initialize it, clean up, that sort of thing.
Sorry,
yeah.
Question. The fix is that corresponding to what was n in
the
version? Okay.
Exactly.
So you still do explicitly pass in the number.
Yeah.
It's not just like part of a sugar that goes in with AP.
Yeah, so you still have, due to sort of, you still have to have fixed there. You don't need to like name it fixed or anything like that, but you do still have to have a function. The VA list can't be the first function or the first argument. There has to be some sort of like fixed argument for
on
that.
The rest side, just rest, even though you're having a lot of sugar here, like you still do have to have that explicit number. You can't like export something.
It doesn't. Yeah, so you have to have some sort of like fixed argument. It doesn't have to be the number. Sorry, I didn't talk about that earlier, but it doesn't have to be the number of arguments. It could be anything. Like it could just be like,
it's
so
just,
here
it's just as a result of how you're doing things, there has to be a first argument.
No, it's due to the way that VA lists are implemented. There has to be like, just in C, and the way it's defined in C, there has to be some sort of first argument. It gets crazy. There's tons of architectural details I can talk to you about for hours about. But the original legacy reason was something sort of along the lines of that. It was the last function argument that occurred before the rest of those.
And then on the part about positive not having to explicitly initialize it, does that mean that like there can only be one initialized in this function? Is that like part of the concern? So like you don't have to worry about people trying to double initialize it,
or not clean it up, or it also then it can't escape from this function because it's internal. Like it's it's allocated internal to that function, so it absolutely cannot escape that function. So yeah, due to concerns like that, and we just, again, uninitialized memory is just not a great idea. So yeah, we just wanted to avoid that. And it's just, I mean, it's just easier to write it this way. So it's a little more work on the compiler side, but that's always better to do it there. Great questions. Any other questions? And by the way, if I misstate something, I'm sure I have misstated things. Please correct me. Some more things. So we just talked about this again. So in those functions like that, we absolutely do not want the VA list to be able to escape the function, and then we also don't want VA list to be able to escape from closures, because inside of like the AP copy implementation, I can actually show you. Here, right? So we call VA copy, we run the closure here, and then we call VA end afterwards. So if the VA list escapes the closure, it's already been cleaned up. So that'd be a very bad idea. Awesome. So now let's get into the nitty-gritty details. This is the fun part. And this is the why, well, we've kind of already talked about why you should never use VA list, but this is really when we get into it. The VA list structure actually varies based on the CPU architecture. And basically it narrows down to there's a lot more than this, but we've currently only implemented like these 4 basic types. There's a character/void pointer variant where it's essentially just like a pointer to a block of memory. There's the x86-64 ABI, the AR64 ABI, and the PowerPC ABI. Enter Windows. Windows and iOS are always a character/void pointer. So even if you're on like AR64, which has a specified like structure, it doesn't matter. You're using the character/void pointer variant. Ironically, like it sort of can be considered as a feature, maybe, but they chose that for very specific reasons. But it's just an extra thing. So it makes implementing VA lists very, very complex because you have to it's very dependent on like the architecture, the OS, lots of different things like that. Cool. So let's dig into a case study. So let's say we had a function, a variadic function that was given the arguments 10 and 1, well, an unsigned long with the most significant bit set. So we have a 64-bit value here with the most significant bit set. And I guess this is little endian, so it's probably like an I686 or something like that. And so this would be sort of like our memory layout, right? So we have our first argument here, 10. So you see we got 10, value is 10, and we got like 4 bytes. Then we've got our second arg here, unsigned long, so it's 8 bytes, and the most significant bit is set. So let's kind of walk through what would happen as you go, if you were to have like some sort of function that ran arg with I32, arg with the U64, and arg with another I32. Cool. So originally the pointer is obviously going to start over there on the far left. We'll call, the first time we call arg, we're going to read the next 4 bytes. We'll increase the location, and we'll return those bytes as the type that you requested. If you were to run it again, increment it by 8 bytes, and return the value back to you. If you run it again, sure as everyone has already guessed, boom, you go out of bounds. And if you're familiar with C and pointers, this looks a lot like your typical buffer overflow.
Specifically the character void pointer.
Yes, and close enough. We'll get into it in just a second. Literally one more slide. But yeah, it's just as a whole. If you call VA arg too many times, like we did here, you're gonna go off the end. Like it's just like a typical like pointer, more or less. Yeah.
So how does VA list actually tell when the list is?
there's no like thing that says this is the end. It's up to the programmer. So it's just to make sure that you call it a certain number of times. So that's what those format string boolins and things like that are. That's what they actually do. Is it's essentially just they somehow force VAR to run too many times, and then it just kind of it's the same thing as a buffer overflow. Then cool. All right. So now let's dig into mixing types. So someone else mentioned earlier about how there's no enforcement as far as like you can pass in an integer and then request like a float, even a pointer. Let's see here. So this is the same, right? This is literally the exact same list. We've got 10 here. We've got that set here. We've already called arg with I32, and now we're going to call arg with an F64. It is an 8-bit value that's left. So essentially all that's going to happen, and this is still assuming 32-bit x86, will just essentially read that chunk of memory, increment the pointer by 8 bytes, and then return that to you like it was a double. So you'll get -0, the most significant bit set. That's pretty bad. It's not the worst, but it's pretty bad. However, let's say that you're on AR64. AR64 and like the x86-64 ABI, they're actually both very, very similar. They have two members. So it's like a complex structure. So there's going to be the GR top, and that's going to be like general registers, and so that's where like your integer registers are. And since pointers are integers, like if you're to pass a string, that's where it's going to be. So that's where your integers are going to be. But then you're also going to have the VR top, which, remember right, it was like vector register maybe? They have another variable called VR top, and that's where your floats are going to be stored. So then here, what we called arg with I32, and we've incremented the right one. But then if we call it with F64, we're reading and incrementing the wrong pointer. You're going to go out of bounds. Not great. So it's short. Be nice to your computer, and be very, very careful with VA lists. They're super, super complex, and just like pointers, they're super easy to abuse and misuse. Really think of them kind of like a pointer, because that's really what they are. And it is super, super, super unsafe. So don't use VA lists in Rust unless you absolutely, absolutely have to. And if you do, be very, very careful. So just some acknowledgements. Eddie B was incredibly helpful through the review process. I literally took a year on it. He was incredibly patient, and I'm still a Rust compiler newbie. He was really helpful, and we went through like at least 4 complete rewrites of the PR. So super, super helpful. And there were a ton of other people that were really, really helpful with the PR. And that's it. So any questions? Yeah.
You mentioned that you shouldn't use VA lists in Rust unless you absolutely have to. What is the use case in which you'd actually want to use it?
So like relibc. So like, which was the reason why I wrote it in Rust, is rewriting a libc in Rust. Like you can't do that unless you have VA list. And there were lots of other people who were requesting it and like waiting on it. So
great. Like
but
if you say like, hey, I have this C library.
Yeah.
Like a good use case for Rust. Can you replace it with Rust and it will work? And if you have like one function in the C library that's using this for the call pattern,
yeah,
you can't replace it unless
yeah, exactly.
So it's mostly for just rewriting C libraries and binary.
Or like if you wanted like, yeah, or if you were writing some sort of interface for C, right? That it only makes sense if you're doing something with C. If you're on that FFI boundary, which is why it's in the FFI. I mean, it depends. I would actually probably not, and I would probably use make the user use a default, like make 0 the default if you're going to do integers. Yeah, I would try to avoid it, honestly. So it's kind of weird, like spending a year writing code that you're evangelizing people to not use. But there are there are very specific use cases, and it's those like unfortunate use cases that you're just trapped unless this happens. So I basically did this for the people who are trapped, essentially.
So I know that Tyler isn't really going to be able to say, but is there even any level of programming theory that can keep your Rust code safe against even careless or malicious C VA-less calls?
So you mean like? Yeah, I mean, so it like if we go back to like
if I'm writing a C library, is there any way I can actually protect myself from VA-less calls?
Like in C that we're just like horribly wrong. It's
It sounds like a horrible
yeah, pretty much.
Right, like if you have a type that isn't total, that it doesn't, right? Like not every arrangement of bits is a valid instance of the type.
Yeah.
If you see an invalid arrangement of bits, you could say, I've gone where I shouldn't go, but like you're still kind of screwed.
Yeah,
like, what do you do?
It's just not great. You're really, it's not the best interface. It made sense at the time, and there's lots of stuff that uses it. So another really, sorry, were there any other questions?
So I guess you're letting the compiler call free on the list and give it us.
So you're talking about like, so it's not actually free. Most of the time it actually does nothing, but you are LLVM. So we're using the LLVM intrinsics for those two, but LLVM, it's written in like the LLVM spec that you must call this. So we just put it in there, but most of the time it actually does nothing. But
so is that why they add that passing the list to the VAD?
So the reason why I can't write add-in now is just because I haven't implemented it yet. I'm literally like in the last little bit of cleanup before I submit a PR for doing that, so that you can write add-in.
I mean, it has any data in the VA list has to live exactly as long as the function.
So
because it's passed as part of the function call.
Yeah. So okay. Yeah. So you're talking about like from an FFI perspective, like v-add-n. So whenever you write v-add-n, you do not call VA list at all, and that's not injected by the compiler. That was probably confusing. Yeah. So the implementation we wrote here, v-add-n. Yeah. The VA end is not called at any point here for you. It's specifically whenever you're dealing with like the VA copy. That's the only time currently that we're actually injecting. We have that VA end.
For the implementation. Okay, so the only time you actually work with the VA list is the implementation on the students started.
Yeah, that's it.
Okay.
Yeah. Sorry if I misunderstood your question. Yeah. Another just kind of funny, interesting note. You'll actually note that this is an 8-byte value that's aligned to 4 bytes. I was hoping somebody would be like, that's incorrect, but that actually does happen. I actually found that out as I was doing this PR and testing Windows. In every other case, x86, a 32-bit x86 aligns 8-byte values to an 8-byte boundary, except for VA list. Apparently they pack it. And so you have 8-byte values at a 4-byte alignment. So this actually meant that we were using the VAR intrinsic the whole time until we hit this, and then we had to rewrite the implementation completely ourselves in LLVM IR. It was pretty gnarly. Well, any other questions about that? Yeah, Windows x86 13. So they are because I didn't talk about that earlier, but the x86 32 VA list structure is the character pointer, and so that is the technically correct one. But that's just this weird thing where everywhere else they 8-byte align 8-byte values, which is what you should do, except for right there. So yeah, what can you do? Please test my code. If you find bugs, please report them.
Do you have a repository for this?
So this is in Rust or Rust. So just Rustling Rust.
Yeah, I mean, do you have we'll post a link to the slides.
Oh, the slides? What?
Yeah, I believe right now.
Yeah, the slides are on my website. So if you just go to dlrobertson.com/slides, you should see it here. and it's December 14th. So
How do you find the PR process? Like day one, you're like, hey, I'm going to do this. Did you just open up a PR and
so
submit it, or was there some like?
so I didn't submit the
Yeah.
So see, it was a really long, weird process. I did not think I was going to do this at first. It just sort of happened by happenstance. I was currently working on RelibC, and I was doing stuff for them, and we were just hitting so many roadblocks with VA lists. I was trying to help them get started, and we were just hitting so many roadblocks with VA lists. I was like, forget this. I'm gonna do it. And there wasn't any progress in the issue, so I just kind of picked up the issue and started researching the issue. And actually, currently, there's a crate that does almost everything that I just wrote in core Rust. Yeah, it's just different. And so I was contributing to that, but we were just kind of getting to the point where we really needed it in Rust. And so I started researching the problem for probably like quite a few months, and being on, getting on the chat channels and talking to people and getting advice about it. And I mean, whenever I first started this PR, I was like super new to Rust. I think I'd opened like 2 PRs that were like, adding a test and fixing a typo in a panic or something like that. So I had to learn a lot about the compiler, which if you're interested in learning about the compiler, there's the Rust C guide, which is amazing. And if you're interested in working on the compiler, come talk to me afterwards and I can give you more pointers. But yeah, so I researched the problem for a long time, got on the chat channels, talked to people, and I got a ton of advice from a lot of people about sort of like how to attack it and like where to go way before I opened the PR. This was an interesting case because it was from like an RFC, right? And it was an RFC that I wasn't involved with. But this particular RFC mostly talked about the like interface. And they did a really good job like hashing out the interface, right? So making sure, yeah, and like making sure that it like there's no way a VA list can escape the closure, like things like that. But
Sure, GitHub account.
DL Robertson should be if you go to the first page of the slide, it should be this one right here.
Okay.
Assuming with my dog. Sorry, what was I talking about?
It laid out the interface.
The interface and the
Yeah.
RFCs, that was all.
Yeah, so a lot of that was already written out,
Nice.
and they did do a good job with writing out stuff like that. But yeah, if I were to do it again, I probably would have started by picking out like an ICE or an entire compiler error. Those are really great issues. And I kind of did that after I started this PR to learn more about the compiler. I picked up a few ICEs, tried to fix those.